Hello everyone, this is group number 4, and our topic is about investigating the traffic accident severity in Montgomery County of USA. According to WHO, approximately 1.3 million people die around the world in traffic accidents annually. Based on United States Department of Transportation in 2021, 49,915 people died in traffic crashes in the United States, and in Maryland state fatalities increased by 8% from 2018 to 2021. Montgomery County, as a part of Maryland state, was suffering as well. The consequences of this phenomenon led to the enormous economic, social, emotional, and health issues for humans. To address this issue, the county developed a plan called Vision Zero 2030, aiming to end the serious injury and death on its roadway by 2030, and assigned a 6 year budget to bring this safety project off the page onto the road. Given this situation, the county is welcoming to new innovative solutions.
There are numerous factors related to driver, vehicle, pedestrian, road, and weather that affect traffic accident injury severity, what we call it TAIS. However, the problem is that the county gathered a high volume of data related to TAIS, but lack of in-depth analysis. So our motivation is to undertake a data-driven approach to TAIS analysis and reduce damage in Montgomery County to capture this objective. The accident data from January 2015 to February 2023 containing detailed traffic information of collisions in the county was gathered from an open data source. This data was collected using the automated crash reporting system of Maryland State.
The collected data had 4 datasets including driver incidents, non-motorist, and pavement plus weather conditions as an external dataset. So the warehouse was created based on these datasets. We also utilized GIS libraries in Python to merge the pavement dataset with other datasets. The procedure of data preparation starts with extracting the number of attributes, data points, data types, and missing values. Then all 4 datasets are flattened for driver analysis and 3 datasets for pedestrian except the pavement dataset. Having gone through the literature, some factors were eliminated. Afterward, duplicated data points considering all attributes were removed. Only categorical data had missing values, which were filled with mode to have clean datasets for modeling. Finally, explanatory data analysis was applied to better understand data distributions and give us insight. To do so, we benefited from descriptive statistics and several visualizations. The quartile diagram was used for abnormal detection of 4 numerical attributes. Regarding the driver dataset, by using the heat map diagram, we realized that the rush hour on weekdays is higher than other times. This shows that the analysis of crash severity in a time series manner can be beneficial. For the pedestrian dataset, we were also curious to understand the effects of pedestrian movement on pedestrian accident severity. Since the result verifies this impact, we decided to consider pedestrian characteristics and actions to analyze and predict pedestrian crash severity.
Our first objective is to discover the key attributes that contributed to the TAIS. For this purpose, we will use the decision tree algorithm, as the target variable has discrete values representing various levels of injury severity. To obtain the importance of the variables, a measure of information gain will be used. Once we identify the important factors, we'll use K-mode clustering technique. After getting the appropriate segmentation of the dataset, our next task will be characterization of each cluster and applying association rule mining to realize what patterns are governed in terms of crash severity in each cluster. By rule mining, we can extract hidden relations between various attributes in a large dataset like accident data.
For objective 3, we are going to predict TAIS for both driver and pedestrian. To do so, 2 algorithms have been chosen, naive Bayesian and K-nearest neighbor. The crash severity for both driver and pedestrian will be predicted based on important attributes recognized in objective 1. Then the best classifier will be determined based on model evaluation. We are following the 3 remaining steps based on CRISP-DM. First, developing 3 classifiers, 1 clustering algorithm, and association rule mining. Next, all models will be evaluated. At the end, it is expected to deploy the results of this research as a part of a preventive action system. For validation, the supervised classification models will be evaluated by ROC curve, AUC, and confusion matrix. For unsupervised techniques, sum of squared errors, Davis-Bouldin index, support and confidence are considered for checking the goodness and evaluation of models.